Oh, it's 20. Okay.
So many chapters.
Then we don't have to do it actually.
Okay, great. Even better. Okay, other questions?
Oh man.
Okay, so today we're going to finish up 4.1, and the important thing here is something called the mean value theorem. I mean, there's actually a lot of important things in this section, but maybe the one that's central is this idea called the mean value theorem. So it's going to seem kind of out of place, like this is a result, but this result is actually central to everything that follows. It's basically, I said a couple times, the most important theorem in differential calculus. Okay, so to get to the mean value theorem, we start with something called Rolle's theorem. Rolle's theorem. Does anybody know what Rolle's theorem says? Can anybody sort of roughly give a rough impression of what Rolle's theorem tells you? Yes?
Isn't it if there's an equation and on two separate x's there's the same y, that means somewhere in between the slope must be 0?
Yes, yes. Okay, so here's the picture, right? So if you have a function that obtains the same values at the endpoints, then somewhere in the middle, there must be a place where the derivative is 0. Okay, there must be some place in the middle where the derivative is 0. Okay, so that's not necessarily true if your function is not differentiable. For example, you could have something like this, right? Something like this. Okay, has the same values, but there's no place where it's 0. Okay, so we have to. It's only true for this is only true for certain functions. Yeah, Noor.
What do you mean, like something is 0, like the slope?
Where the slope is 0.
The slope is 0.
So for this, you need more than just the endpoints being equal to ensure that the derivative is 0 in the middle. Okay, and so what you need are the following conditions. So you have some function on a closed interval. Okay. If f is continuous on the whole interval, if f is continuous on the whole interval, is differentiable on the interior of the interval. This is called the interior of it, and f of a equals f of b. F of a equals f of b. Then there's a place, C, in the interior where f prime of c equals 0. So there's a place where f prime of c equals 0.
Wait, if f is continuous on A and B.
Continuous, differentiable, continuous on the whole interval.
Yeah.
Differentiable on the inside, and f of a equals f of b. So if all three of those things happen, then you're guaranteed a place where the derivative is 0. Okay, and so the picture is, what I just erased, right? You've got A, B, you've got this thing, right? And there's going to be some place where the derivative is 0. Okay. So that's geometrically. So this is maybe graphic interpretation. Okay. As for physics interpretation, if you're thinking of f as position, okay, if you're thinking of f as the position of a car on a track, okay, so here's f, right? The car is moving along the track, right? And t is in the time interval a b. What is? Can anyone interpret what Rolle's theorem says in terms of the car? So you've got this car, and f at time a equals f at time b. Then Kayla.
Is it that like if they start at the same speed, or start at the same, I don't know, I guess speed would be the word I would.
So f of a equals f of b, right? What's f? F is position, right? So f at time a equals f at time b. Amanda?
The velocity at c is going to equal 0.
So if you have a car that starts at one point, starts at some point, moves around, and then comes back to the same point at the end of that time, then there must be some point where its velocity was 0. Okay, in other words, it must have turned around at some point, right? And at that turning around point, right, this car goes forwards and goes backwards and then comes forwards again, right? When it went from going backwards to going forwards, then its velocity must have been 0. Okay, so that's it seems very trivial, right? Either a car that starts and ends at the same point on a linear track, then it must have turned around and stopped for just a second. Okay, so that's all Rolle's theorem says. Okay. So there must be some time c where the velocity is 0. The velocity, instantaneous velocity is 0. Okay. Everyone getting a sense of what Rolle's theorem says? Okay. Anyone have questions? Okay. So why is it true? Why is it true? Why is it true? Well, let's think about it. Here's A and here's B. You have your car, starts and ends, right? Where is the why is there going to be a place where the velocity equals 0? Can anybody say it? Why is there going to be a place where the slope equals 0? Why do you guarantee the place? Or let me say it this way: at what place is the slope going to be 0? Or what kinds of places are the slopes going to be 0? Anur.
When you're going at a constant rate.
When you're going at a, what do you mean you're
Like your
going?
velocity is like.
Your velocity is a constant rate. If your velocity is a constant rate, then actually you're going to look like this,
yeah.
right? Because you're, right? So no, not exactly. Sarah?
When you have a max or a min.
When you have a max or a min, right?
Or or the whole thing if it was just like a straight line.
Yeah, so yeah, it could be, maybe the thing is flat, okay. So that's the idea basically. Why is it true? Basically, because of the extreme value theorem. Because of the extreme value theorem, right? You're gonna have the right. You guarantee a max, right, and a min, right, and at those points, the slope is 0. Okay, so that's the idea. But I'll lay out the actual argument more precisely right now in a second. Okay, so here's the picture, right? You're trying to show that if your function starts and ends at the same point, then there's some place in the middle where you have a slope of 0. But by the extreme value theorem, you know that there's going to be a max somewhere, and
Sorry, I just.
Yeah.
Sorry. Thank you.
okay, it's okay. By the extreme value theorem, you know that there's a max somewhere, and from what we said last time, you know that the slope is going to be 0 there. Okay, so let me lay it out more precisely. There are actually two cases. So case 1. Case 1, the global max and min occur at the endpoints. The global max and min occur at the endpoints. What happens in that case? What can you say? What do you know about your function in that case? If the max is at the endpoint and the min is at the other endpoint, what can you say? What can you say about your function? Luke?
It's a gradual rate of change.
Here's the hint. F of A is equal to F of B, right? So F of A, so the thing to keep in mind, F of A equals F of B. Suppose one of those things is the max value and one of those is the minimum value. Well, what's your function?
It's flat.
It's flat, right? Because in that case, the maximum value equals the minimum value, right? And so all the values must be the same, right? So in that case, f is a constant function. Right? In that case, f is a constant function because this value is bigger than or equal to all other values, and this value is less than or equal to all other values. Well, that means that all values are the same. Right? Is that clear? Is that clear? Anybody confused on that? Right. If I say all my values are less than or equal to, or all my values are bigger than or equal to 1, and I say all my values are less than or equal to 1, well then all my values must be equal to 1, right? So that's what we're saying here, right? Yeah. If the maximum value and the minimum value are the same, then your function is flat. Okay. So in that case, f is a constant function, and if f prime is 0 everywhere, right? So so we're good. Remember, we're looking for a place where the slope is 0. Well, we're looking for a place between A and B where the slope is 0. It's 0 everywhere. Okay, so we're more than good in this case. Okay. Case 2, the global extrema are not both at the endpoints. So they're not both at the endpoints. Maybe one of them is at the endpoint, but the other one is not. Or maybe they're both not. Okay. But in any case, we're not in the case where both of them are at the endpoints. Okay. Well, in that case, what happens? Let's say like the max is not at the endpoint. Then where is the derivative equal to 0? Jennifer? At the max. Exactly. Right. So, for example, suppose the max occurs in AB, then f prime, the derivative there is 0, right, by Fermat's theorem. Right. And so that's, so you've found the point, you found the place where the derivative is 0. Right, so the picture in the first case turned out to be like this. The picture in the second case is like this, maybe. So the minimum, maybe the minimum is at the end, is at one of the endpoints, right? But the max is in the middle, and so that's the guy you're looking for. You found the place in the interior where the slope is 0. And that's Rolle's theorem. In either case, you found there's got to be a place where the derivative is 0.
That's it. Occurs after the max.
Occurs in AB. Suppose the max occurs in AB. Okay, so Rolle's theorem tells you, right, that you're guaranteed a place where the derivative is 0. Okay? As long as these conditions are satisfied. Okay. So maybe we'll give you a problem. Okay, so here's a problem for you. The polynomial x cubed minus 3x squared plus 4x minus 1 has only one real root. So show it, or show that, or explain why. Explain why this polynomial has only one real root. And the way you want to, here's one possible strategy. Suppose there are 2. Suppose there are 2 roots. What would happen? This is a little bit of a tricky problem. I'll let you think about it for 2 minutes. Two points on the exam if somebody comes up with the answer. Does anyone have an idea? Anyone have sort of a strategy at this point? Amanda, go
What
ahead.
do you use synthetic division to try to get the root? Okay. Well, you win some,
Yep.
you lose.
So the other hint is we've just been doing rules now. Right, this has to do with rules. Sarah, yeah.
You're gonna first take the derivative and then factor.
Okay. So take the derivative. So let's call this thing p prime, 3x squared minus 6x plus 4. Okay.
And then I would factor, but well,
Can you factor that? If you can, you're really impressive.
Yeah, that's what I can't do.
Okay, so let's use a quadratic formula. So like,
3.
what?
Would it be plus 3 because you're minusing 1 on top?
3x squared minus 6x plus 4, right? What quadratic? What
Oh, never mind. That one.
Okay.
Never mind.
Okay.
It's not plus one.
Okay. Luke, you have a question?
None.
Okay, so let's use the quadratic formula, right? Right. The roots are negative b, right? Plus or minus the square root of b squared minus 4ac over 2a, right? Okay, and so what do you see? Right, you got 6 plus or minus the square root of negative 12 over 6. Okay. What's... Okay. Okay, can anyone see the punchline? Can anyone see it? Raina, yeah, go
You
ahead.
can't have a negative in the square root. So
Well, you can, but
Yeah.
these are complex numbers. So these are complex roots. These are non-real roots. Right. Non-real roots. Who sees why that's a problem? Who sees what that has to do with the question that this thing has only one real root? Evan.
If the derivative is never 0, then that means that the graph won't change direction, so it will always go up. Basically, like, the numbers will always be increasing.
Okay.
So it can only touch 0 on the y-axis at one point.
Very good. Very good. Okay. Yeah, good for you. So did people see what Evan's saying? He's saying, well, look, if you look at the values of the derivative is never equal to 0. Right? So that means that the values of the derivative are either all positive or they're all negative. Okay. Right, and you see that, in fact, they're all positive. So you see they're all positive, and in fact, it's a graph some sort of graph. Okay. So in that case, your function is an increasing function, and so it can have only one real root. Right? So p prime is always greater than 0. So p is increasing, and thus can only have one root. Right. And you can check values to know that it's negative somewhere and it's positive somewhere. So it has to have one root, and it can only have one root.
Wait, is that the graph of p prime right there?
Yeah, p prime. P prime is a parabola that is positive and never touches the axis, never touches the y-axis. Everyone, does that argument make sense to people? It's a little bit tricky. Good job, Evan. Another way of seeing it is like this. You could say, so the way that I would have done it is like this. Say there are two roots of p. That means that p is 0 in 2 places. P is 0 in 2 places. So what? p is 0 in two places, then what do you know?
The derivative must be 0.
The derivative must be 0 somewhere, right? There must be, by Rolle's theorem, p prime equals 0 somewhere between. Somewhere between the roots, right? But p prime is never 0, right? So we couldn't have had two roots, so we could not have had two roots of p. Two roots of p mean that p prime is 0 somewhere, but p prime is never 0. Anyone have questions? This is maybe more abstract an argument than we've been giving recently. Anyone have trouble with the logic of this argument? Yeah, Ellie.
I just have a question.
Yeah.
Is this going to be on the test?
No, this is not on the test. So everything up until last class and last class's homework will be on the test. Okay, let's go on. Okay, so now the all-important mean value theorem. It goes like this. You have some function, again, you have some function on an interval AB, and f is continuous on AB and differentiable on the interior. And we don't say anything this time about the endpoints. Okay, so no constraint on the endpoints. Then so you have some function that looks like this, say. Right, the endpoints don't have to be the same value. Does anyone know the statement? What can you conclude?
The derivative is 0 someplace.
Well, does it look like the derivative has to be 0? Not in this picture. Win, go ahead.
Isn't it like the slope of the tangent line of those 2 points, then there must be a derivative of that line with the same slope of the tangent line, right?
Yes, well, we call this thing the secant line.
Secant line,
yeah,
yeah, that's
so
it.
the slope, if you look at, so the conclusion is this. If you look at the slope of the secant line, there's some point where the slope equals the slope of that secant line. Okay, there's some point where the slope of the tangent line equals the slope of that secant line through the endpoints. Okay. So there exists a place where f prime of c equals the slope of the secant line. Well, the slope of the secant line is f of b minus f of a over b minus a. Okay. So there exists a place, c, where the slope, the instantaneous slope here, equals the average slope. We can again give a physical interpretation if we think of f as position and our variable as time. Okay, so time in some time interval, t in some time interval. So what does this say in terms of velocity? There's some place where the instantaneous velocity.
Equals the average.
Go ahead, Annette.
Equals the average velocity.
Equals the average velocity, right? There's some place where the instantaneous velocity equals the average velocity over the whole time interval. right? So there's someplace, there's a time when instantaneous velocity equals the average velocity over the interval. Okay.
That position at
Position? Okay. So if you drove 60 miles in an hour, then at some point you must have been driving exactly 60 miles an hour. That's all that this says. Right. If you drove if you drove for an hour and in that hour drove 60 miles, then there was some point in that interval, in that time, where you were driving exactly 60 miles an hour. Okay. Again, it's not, doesn't seem like a very, impressive statement, but it's, it actually is. Okay. And any questions about this statement? Any questions about the statement?
Can you say it one more time?
Yeah, sure.
Like just in your own words.
Yeah. So you have a function, right? You have a function. It's it's continuous. It's differentiable, right? What it's saying is that if you look at the slope of this line between, so here's your function. Okay. If you look at the slope of this line and you write it down, say the slope is m. Okay. Mean value theorem tells you that there's some place where the slope of the tangent line equals m. Okay. That's it. The slope of the tangent line must have equaled m somewhere inside there. That's the same thing as saying here. Okay, so why is it true? Why? Why is this true? Okay. Hold on for a second. Okay. Yeah, please don't use your phones in class. Please don't use your phones in class. I see there's a bunch of you using phones right now. Over the summer, I was teaching in China, and it was sort of astonishing to me that the Chinese students, like maybe a third of them, were using their phones in class. And I thought, oh, maybe they all sort of know the material, and they don't need to pay attention. But then they took the exam, and it turned out the ones who were using phones in class all failed. So the second week, I sort of cracked down on them. I said, okay, no more phones in class. But it was really strange because it turned out that they were extremely addicted to their phones. They couldn't stop using their phones. They would just talk constantly on their phones. And so one time I came in, I told them the story about how it's impossible to focus on two things simultaneously. You know, the experiment with the man in the gorilla suit, right? Right, so they do psychological experiment. They say, watch this video of people playing basketball. Count the number of passes. So they, okay, everybody's counting the number of passes, and then they finish and they say, okay, who saw the man in the gorilla suit? And everybody, some people say, what are you talking about? They rewind it, they play it again. Right in the middle of the basketball game, a man in the gorilla suit walks through, and nobody saw him. Nobody saw him, because they're all focusing on the passes. Okay. And so this is basically a demonstration that the mind can't focus on two things simultaneously. And you don't want to be like focusing on trying to focus on one thing and trying to focus on another thing at the same time. It's just doesn't work. You can't do it. Right? You might think my brain is somehow better than other brains, but no, your brain isn't better than brains. Right? We all have basically, roughly speaking, we have all the same brain. So I told this story to the class, I said, so no using phones in class. I turn around, 5 minutes later, I turn around, people are using their phones again. And so at that point, I said, okay, give me your phones. And then, so I took the phone away from the one person who's doing this. Next time the kid comes to class, he's using his phone again. I say, okay, give me your phone. No, in fact, get out. And that's the first time I threw a student out in my whole teaching career of 20 plus years. But then, that afternoon I threw another student out. The moral of the story is don't use your phones in class, please. Okay. Yeah, otherwise I'll have to, throw out more of you. Okay, so why? So here's the thing. We use Rolle's theorem. So here's the picture. And you might think, well, how can we use Rolle's theorem? Right? How can we use Rolle's theorem? Right? Rolle's theorem talks about when you have a function that's equal at the endpoints. Right? Function that's equal at the endpoints. But here you have a function that's not equal at the endpoints. Does anyone know the trick here? Anyone know the trick? Yes, Sarah.
I don't know if it's really a trick, but I mean, you can imagine visually that if you just took that line and flattened it out, that it would be Rolle's theorem would then apply, whereas it's basically the same. You're just calling whatever the slope is, that's your new slope of 0.
That's sort of it, although it's actually not a rotation. So I think what you're sort of saying is that you just rotate the whole thing.
Yeah.
Right? But it's actually not a rotation, but it's sort of like a sliding of it. Okay. And the sliding is achieved by as follows. You say, consider, so let L be the equation for the secant line. Let L be the secant line. Okay, so you have this function L here. Okay. Here is F. Here is F. Here is F. Okay. So, and here's the trick. Let you introduce a new function d, and it will be F minus L. So the d stands for difference. D is going to be the difference between the original function, between your actual function, and this function, the line that we have here. Okay, so what do you see about D? What do you see about D? Who notices the key fact about D? Isaac.
Sometimes it's positive, sometimes it's negative, given the difference in between F and L.
Okay, sometimes it's positive, sometimes it's negative. Anybody notice other things about D? Amanda? Anything related to Rolle's theorem about D? What is D of A? What's D of A? At least?
Would that be the minimum?
Well,
Or
so
does it have to do with the extreme?
D of A is going to be F of A minus L of A. Right? So what's the difference between the function and the line at time A?
0.
0. Okay. Right. And? Jennifer?
It turns it into that function where L of x would be like the x.
Exactly. Right. So notice that D of A equals D of B. Right. Further, D is continuous on AB and differentiable on the interior. Right. So we can use Rolle's theorem on it. So Rolle's theorem says what does Rolle's theorem say? Everybody take 1 minute and just see what Rolle's theorem tells you in that case.
little bit confused
Yeah.
about how you got d of a equals d of b.
They both equal to 0. Right? So d is the difference between f and l. And if you look at it, f and l have the same value here. Right? F of a and L of A are the same, so D is 0. Here also, right, F of B and L of B are the same,
Yeah.
so D is 0. So D is 0 here and D is 0 here. Right, if you look at the difference
Why
function,
is this the difference?
looks like this. D looks something like this.
Okay. Thank you.
When, are you gonna give the punchline?
Maybe?
Okay, are you gonna answer the question?
Yes.
Okay. Who would like to answer the question in addition to Win, other than Win? Go ahead.
So Rolle's theorem would say that then the derivative of d of some number c would equal 0, and if we took the derivative of d of x, then it'd be the derivative of f of x minus derivative of L of x. Since L of x is a line, then the derivative is constant, which means the derivative of d of c equals 0 is when the slope of the tangent line is equal to the slope of the secant line.
Exactly. Right? So Rolle's theorem tells you that the derivative of d is 0 somewhere. But what's the derivative of d? It's the derivative of f minus the derivative of L. Right? So this equals 0 at that c. Right? This equals 0. Right? In other words, f prime is, there's a place where the slope of the tangent line of f equals the slope of the secant line. But the slope of the secant line is f of b minus f of a over b minus a. And that's what we wanted. We wanted to find a place where the slope of the tangent line equaled the slope of the secant line. Okay, that's it for today. So exam next class.